Our autonomous first detects our team object using an ultrasonic sensor, then pushes the purple pixel onto the spike mark. Now it's going to the board to place the yellow pixel on the corresponding spot on the backdrop, and then park.
The robot faces each spike mark position and then takes input from the ultrasonic sensor to see if there's an object within range. If there is, it knows the team marker is there. The ultrasonic sensor keeps things simple and is multi-purpose as we use it at the backdrop here. You can see small adjustments the robot makes by reading the ultrasonic sensor's values to make sure it's the correct distance away from the backdrop.
While scanning for the team object in the center position, you can see it wiggle left and right. This scans a wider area to ensure it doesn't miss the team object if it's on the center spike mark.
Since our robot is farther from the backdrop in this position, it waits 5 seconds to ensure that there will be no collisions between our robot and our Alliance member's robot.
If the team object is placed on the left or right spike mark, then we won't be able to go on the same path as we did previously because our Alliance member's object would interfere with our robot's path. Because of this, we reverse before going through the truss. To make sure that we wouldn't collide with our Alliance member's robot while doing this, if they don't have an autonomous, we will ask to position ourselves closer to the backdrop.
As the robot drives towards the backdrop after placing a pixel on the left or right spike mark, there's a risk of collision with our Alliance member if they are parked in the corner. Therefore, the robot stops earlier and strafes towards the backdrop to avoid our Alliance member's robot and mitigate this risk. Here, we have the macros that set the arm to positions that allow the robot to place pixels on the board, hover above pixels to line up the claw, pick up the pixel, and reset the claw to its original position. This is a more efficient way to pick up pixels and place them on the backdrop.
We are using heading correction for our autonomous and TeleOp periods in order to keep our robot straight and make turns sharper. Here, a team member is moving the robot to the left and right, demonstrating this.
Here, a team member is driving the robot with our heading correction. The robot is able to stop quickly from a turn, allowing more precise movements. This allows the driver to pick up pixels easier and allows the robot to stay on a relatively straight path.
In comparison, here is the robot being driven without heading correction. It drifts a lot more, and the turns aren't as precise.